started. So we will continue our discussion on the flash. And the last lecture we talked about one of the mechanisms to inject or eject electrons from the floating gate. And today we are going to talk about the second mechanism, which is this channel hot electron to inject the electrons from the channel to the floating gate. And this one is used by the low flash. So the idea here is that we need to bias the channel with the drain voltage, and typically it's like maybe 5 volts or 6 volts, and then this is a quite large VDS. So the electrons will flow from the source to the drain, but as the electrons travel, so the electron will gain the kinetic energy because of the electric field. And then the electrons will become high kinetic energy as they approach the drain here. So the kinetic energy means temperature in some sense. So those electrons become hot. So that's why this is called the hot electron. So if the electrons become hot, high enough energy, okay. So if we look at the band diagram along the channel, which is this one, from source to drain, and the drain has a large VDS, so the drain is bent down, and electrons basically will fall off this barrier, and then as the electrons falling down, so it will gain the kinetic energy. So essentially the kinetic energy is this energy, because this is band diagram. So this shows the electron's energy. But electron's energy has two components. One is the kinetic energy. The other one is the static, let's say the electrostatic potential, so which is the band edge. But the electrons higher than this band edge is the kinetic energy. So this kinetic energy, if you look at from the other direction, which is this vertical to the channel, so this is the band diagram, vertical to the channel, so the electrons will have this kinetic energy. This is the channel, and this is the oxide, and this is your floating gate. So this is along the BB direction, which is this direction, and AA direction is this direction. So along the BB direction, you also have this KE, this kinetic energy here. So essentially those electrons may have enough kinetic energy to jump over this barrier caused by the oxide. So this is a thermally activated electrons. And then they may jump over the barrier, so then they get into the gate. So this is the hot electron, and essentially as the current flow here, the electrons move from source to drain, but there are some probabilities for the electrons to get into the floating gate over the oxide. So this is called this hot electron, and this is one of the mechanisms to inject electrons to the floating gate. Question?
It's still tunneling through the, or if in tunneling over the gates, right? In this case.
The tunneling to the gate depending on the gate voltage. This one, it may happen even the gate voltage is kind of small. Right? Because most of the electrons travel horizontally, and then they get enough energy, sometimes they can jump over the barrier without going through this tunneling. It's just because they are so hot, so they jump over.
Thermionic emissions.
Yeah, this is thermal activity. Okay, so but here the probability for the electrons to jump over the barrier actually is pretty small, and sometimes this is called the lucky electron, because the electrons has to gain enough kinetic energy and then it may jump over. So the probability actually is small. So how small is it? So we can actually measure this by measuring the transistors characteristics like this. So we can bias this floating gate transistor as we discussed. We apply the VDS, for example in this case 6 volts, and then we can of course have the ID and measure the ID versus the VG here. This is VGS. So we will have our typical ID VG curve. This is in log scale. And then this is just the regular ID VG curve. But if we want to understand the probability for the electrons to inject to the floating gate, we can measure the gate current, IG, here. So this is ID, but then we can measure the IG. So if you measure the IG, you plot it here in the same plot. So you will have this. This is ID, and here this right hand side is IG. So you will see that, for example, when VDS equals to 6 volts, you will see some IG current here. So this current is small. Okay, look at the scale here. It's 10 to minus 10. And your drain current is, here, even 10 to minus 3. So they are very different. So the programming efficiency is defined as the IG over ID. Why is that? Because you flow the current, which is a drain current, by VDS. And then there are some probability for the electrons to jump over to the floating gate that contribute to your IG. But here you look at the ratio, right? So typically here like 10 to negative 6 to negative 8. That means, for example, if the ratio is 10 to minus 6, that means 1 electron out of 1 million electron will inject to the gate. So the probability is very small. So that's why that electron is called lucky electron. So here is another example. When ID is like 2 milliamp, IG is only like 50 picowatt. So this is the ratio. So that's why the low flash, the write power actually will be large. Because when you write the program device, then you flow a lot of current, but effectively only a small portion of those electrons is doing the real programming. This is much higher than the F1 tunneling. So if you look at F1 tunneling, the tunneling current to the gate is less than 1 picoamp, and here is like 50 picoamp. So F1 tunneling is much more efficient because all the electrons, right, will go to the gate. If you recall the F1 tunneling, what we did there, we are not flowing the drain current. What we did there is we apply large voltage, for example 20 volts, on your control gate, and then the substrate is grounded. So because the large voltage difference, all the substrate electron will directly vertically inject to the floating gate. So the efficiency is high. Of course, the turning current is so small there. Less than like picowatt. So any questions here? Okay, so then here just a few more words. We say that the channel hot electron injection efficiency is low. Okay, and we need a large programming current. The ID is large, but IG is small. So here there's an idea to improve this. This is so-called the source side injection, and then it will enable this 1.5 transistor, 1.5T split gate flash. So this kind of design is widely used for the embedded non-volatile memory on chip. This is for the eFlash, which is not the standalone memory. This one is compatible with logic, and typically you will see this kind of eFlash in the product of like a microcontroller. You will have this kind of eFlash to store the codes. So the idea is here. Look at this schematic here. So the problem here, we want to improve the efficiency. But if you look at the electrons, how the electron get into the floating gate through the channel hot electron mechanism, actually there are two steps. The first step is the electron get accelerated along the channel. And only when the electron approaches the drain, due to the so-called impact ionization, so it gets high generation rate. So only when the electron approaches the drain, it will get high enough kinetic energy. So this is when you use a high VDS, you need a large drain voltage to accelerate the electrons. But in this case, you want the gate voltage to be kind of small, because you want most of the electrons to travel horizontally. But when the electron reaches here, then you want to divert the electrons to the gate, right, floating gate. So in this case, then you want high Vg to attract electron vertically. So then this will improve the collection efficiency. So first you generate those hot electrons. Second, you collect the hot electron near the drain. But then you need to boost the Vg. So you see the different requirement on the Vg and Vd in those two steps. So the idea is to combine those two. So then we can have a structure something like this on the bottom. So we have two gates, and it was split gate. And this essentially what we have is this control gate and floating gate. So the floating gate now become accessible. So normally for the floating gate transistor, the floating gate, you don't have direct terminal to the floating gate. But in this case, you want to make a terminal to the floating gate, so you can apply voltage directly to the floating gate in this example. So then you can apply two different kind of voltage. For the control gate, you apply low VCG, and then for the floating gate, you can apply high VFG, and then still you need a large VDS. Then you can see here initially the gate voltage is small, so most of electrons will travel to the drain, and then when they are accelerated and reach here, so you will divert the electron to the floating gate by the large floating gate voltage. So this can increase the efficiency, and this is widely used for the embedded flash. for the non-volatile memory on chip, on the logic chip. Of course, the penalty of this one is a larger cell area. Once you open a contact to connect to your floating gate, you need to pay for some area for the contact. So from the layout point of view, this one will have large area penalty. So this is not good for your high density standalone memory chip. But for logic, it's okay. If you want to have some non-volatile memory on chip with your logic, then you can do this. Okay, so this is for this split gate. Any questions? All right, then let's move to the standalone memory. This again, because our main topic is still on the standalone memory chip. And here we have this two flash array architecture, LAW versus NAND. So this is for standalone flash array, and the LAW and the NAND basically the array architecture is different because the basic cell is still the same, this floating gate transistor. The only difference is how you collect the word length and bit length to the floating gate transistor. So the law is like this. So basically law is something like this, which is very similar as your, for example, DRAM. So using this floating gate, if you replace that with one transistor, one capacitor, it's the same connection because the gate is controlled by the word line, and then the transistor one side is to the bit line, the other side is to the so-called source line. So this is like your DRAM, because DRAM the other side is to the common plate through that capacitor. So it's the same as the DRAM. And this is called law because from the logic circuit point of view, you have the parallel kind of NMOS structure, which is law, right? For the pull-down network, you have the transistors in parallel. So here you have those transistors in parallel. So the NAND, okay, is a little bit different. So the NAND here, those transistors are, those floating gate transistors are in series. Here you see they are in series, controlled by different word lengths. So it's like you have a string, and then for those transistors, if it's in the logic circuits, right, for the pull-down network NMOS, if you have the transistors in series, it's NAND logic. So this is why this is called the NAND. But here there are, let's say, multiple word lengths and control this string of transistor. But the top one and the bottom one, those two transistors are low mode transistor, not floating gate. And this is called the string select. And there are two of them. And then to the top one, it will connect to the bit line. And the bottom one will control the connection to the source line. Okay. So that's a NAND structure. Any questions? Then let's look at the operation. What's the question?
So what did you say the difference was mainly?
The connections.
The source line?
No, you look at the connections of the word line bit lines. The lower, those transistors are in parallel, and here those floating gate transistors are in series. And the way you connect the word line bit line is different.
So how many rows of the...
We will talk about that in a minute. So then let's look at law first. And we need to understand the layout and the operation for the law. So the law actually the typical array architecture is something like this. You can have two cells share one bit line or source line. And if you look at one bit line, then you can draw it something like this. And then if you map to the cross-sectional view of the chip, it will be something like this. And then here, from the top view, the layout is something like this. Okay, so it is just one floating gate transistor. So this is the top view, and then this is the word line, the gate, and then this is source and drain. So you can correspond this layout to this cross-sectional view, and then to the schematic this one, and then to the array architecture like this. So again, the NOR flash, as we discussed before, the programming is by the channel hot electron, and the erase is by the FN tunneling. Okay. So here the only thing I want to point out is that the cell area is like typically is like 5F times 2F. Okay. This side is 2F because this is the bit line direction. So bit line actually will overlap the cell on the top. So like this, the bit line will be over the cell. So the bit line will have 2F because the bit line spacing will have 2F. So the only thing here is that along the source to the drain direction is actually quite relaxed to be 5F. The reason is that the L is not minimal size. The reason is here we have to sustain high VDS as we discussed earlier. For the NOR flash, we use the channel hot electron, and we need to apply like very large VDS, like 5 volts. So for normal transistor, it's very hard to sustain 5 volts. So you have to make the L longer to have this 5 volts. So this L is not minimized, and then you have to share the contact there. So roughly it's like this one is like roughly 2F, and here is F, here is F, and this contact needs to be shared another F. So roughly it's like 5F in total. So then this will give you like 10F square in the cell size. So this is the NOR layout, and then next let's look at the operation principle. So here you need to understand the, let's say, how to bias your word line, bit line, source line to do this erase, program, and read operations. How do you apply voltages? So let's look at erase first. So the erase is by the FN tunneling, as we discussed earlier. And in this particular case, it's based on the source FN tunneling. So that means for this transistor, we want to apply like large voltage, 12 volts to the source, and ground the gate. So electrons will tunnel from the floating gate to the source, and then you remove the electrons from the floating gate. And in the array, what you want to do, here this is a NOR flash array. We just draw 4 cells as an example. So what you can do here is for this source line, because this is the source line, you apply 12 volts to the source line, and then for the word line, this is word line. So word line you ground it, okay. So all the cells which share this source line will be erased, and for the bit line you can open, means floating. So you just will have those FN tunneling happening here. So this is what you do for the erase, and it's in this table, the voltage you apply. And then let's look at the program. So this is the erase. And then let's look at the program. So the program is by the channel hot electron. And as you recall, what we do is ground the source, apply large VDS, in this case 6 volts, and then the gate needs to be turned on. So then you have large current flow here, and then sometimes the lucky electron will go to the floating gate. So in this case, then you need to, for example, for those 4 cells, you can do the individual programming, and you need to select which cell to program. And here, for example, the cell A is the selected cell. If you want to program cell A, then what you need to do is to apply 12 volts to this word line of cell A. And then for the cell A's bit line, you need to apply 6 volts. And then source line you need to ground. So the cell A will be programmed. So this is for